Hello, welcome. This is the asynchronous video, first of two relatively short videos for Thursday, June 11th for Physics 121. We're going to start a new section of the class. We're going to be talking about, we're going to move from the dynamics of Newton's laws and forces to the new dynamics of conservation laws. We'll start with conservation of energy, move to conservation of momentum, and then we'll turn around again and look at rotational motion. But for starters, we need to, in order to actually make some progress, we need to define some things. So our goal for starters is to define some new quantities that we can then use to do the work that we want to do. So we're going to start with a definition of a quantity which we call work. So this is a special quantity. It's a physics quantity, not a, what we mean by work is not the English use of the word, but a special quantity. Now, here's the challenge. The challenge is that, how can I put it? That we need to develop, that is a college-based, calculus-based physics course. Some of you may have learned some definitions of work in your high school class. These are, in some sense of the word, not quite adequate for the purposes that we're doing. If you have a rule of thumb that work is just force times distance, for example, that's just not going to do. We do need a mathematical tool to define work. So the first math tool we're going to look at, actually we need a couple math tools. The main math tool we're going to use right off the bat is the notion of the dot product between two vectors. And so if I have two vectors A and another vector, I have two vectors A and B, and I take the dot product, which is to say I multiply the two vectors in accordance with a symbol, which I write down as a dot, then this is defined as the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between them. So if I have, for example, if this is A and this is B and this is theta, then the dot product is this length times the cosine of this angle. So that's a definition that hopefully you've learned in the past, but we're going to make use of. So now that I've got that definition in place, let me erase this because I want to actually do the definition of work now. So I've got that mathematical tool. So the formal definition of work, so work, and I will usually use a W, kind of a flared W, to indicate work as opposed to weight. And work is going to be defined technically as a kind of integral. And in particular, it's a special kind of integral. So I'm going to label that integral with the little letter C, which is short for curve or path. And I will often emphasize that this is a path integral by putting the word path underneath that integral. And it's going to be an integral on a path from some point P to some other point Q. So the limits correspond to positions P and Q. And what am I integrating? I'm integrating the dot product, which I just defined, the dot product of the force associated with the displacement, infinitesimal dr. And this is the work associated with a particular force. So when I say work is always defined relative to some particular force, and it's defined by this equation here. Now, if you don't know how to do the path integral, don't freak out. We don't expect you, well, we sort of expect you to have seen path integrals in your math classes by the time you get to, say, Math 2 or something like this. But for most students coming into class, the path integral is relatively new. And the happy news, well, or unhappy, depending on how you feel about it, is that we will take some time to unpack the path integral so that you can do the calculation. But let's look at least conceptually what that looks like. So conceptually, I imagine a body that is moving through two or three-dimensional space, and it's moving from a point P, the initial point P, to a point Q, and it's moving on some path. So I'm going to draw the path, something like this. This would be a kind of a, not a straight line path in this particular example. So I've got a body, which I'm representing as a particle. Here's the particle, for example, right here. And once I'm at any given position on this path, there could be a force. So, for example, in this particular circumstances, you could imagine a force that points, I don't know, we'll pick a force that points, say, this way, some arbitrary direction. It doesn't matter. For now, it's just some force that's applied, normal force, weight, who knows what it is, it's some force. And then I'm going to say, well, how do I contend with what this dot product means? What I mean by that is that at this particular position, if I draw a tangential vector corresponding to the change in position, in other words, a vector that is lined up with the tangential direction, dr, and its length is infinitesimal, then the work is basically the integral on this path of this infinitesimal dotted with that force vector, which is to say times, remember, just to remind you here, we'll put this here. So in other words, f dot dr is the same thing as saying the magnitude of f times the magnitude of dr times the cosine of the angle between them, cosine theta. Hopefully you can see that in the corner there. All right. So, so as a rule, this vector, if I'm by the way, what I mean by a path integral, technically, is that I just, every time I take a little step, instead of taking a step, here, the normal integral, I would integrate on a line, a horizontal coordinate like x or t or whatever it is. But here I'm just, the only difference between a path integral and a regular integral is instead of integrating on a straight axis, I integrate over small steps on this path. Every time I take a step on the path, I have an infinitesimal step there. And again, this looks mathematically challenging. You've got a cosine in there, you've got angles, how are you going to calculate this? And the answer is there's a rule for complicated forces that could be varying as a function of position, and for complicated paths, this is technically challenging. But we're going to start with a very specific, we're going to unpack this. I'll tell you, the key, of course, is to use coordinates, so break everything into components. But for now, I will just basically assert without proof that it is a special case, so, which applies to a lot of situations. If the force is constant, which is to say unchanging as a function of both time and space. So in other words, that vector f is like that, and so the same vector here, is here, is here, is here, is here. Everywhere on the path it's the same vector. And also, if the path is a straight segment, right? So it points in some particular direction. I'll label that delta x. It doesn't need to be x necessarily. Just it's a particularly straight path, right? So I'm going to draw that. So for example, you could imagine a vector. This is the path, and I'm representing the path going from P to Q as a little vector that basically goes from here to here, and I'll label that vector delta x. And I've got some force F, right, corresponding to fixed and constant force, and there's some angle theta. Then the work done is equal to the dot product of those two vectors, F dot delta x, which is to say it's equal to F times delta x times the cosine of that angle theta, whatever that angle is between them. That's the definition. of the work done by that particular force F. So again, if you learn your high school definition, this is a force, and that's a distance or a displacement going from P to Q. So force times distance, but a key idea is that that only works if the force is constant, if the path is straight. I can't spell for some reason today, straight, delta x, and it only, and then don't forget the cosine. So in particular, if the force and the, and so let's actually figure out like 3 important examples of this special case. So now I'm looking at special cases of the special case. So if F is aligned, which is to say parallel to delta x, they both point the same direction. So that's F and that's delta x. Then the work is just equal to the magnitude of x times delta x. Make sense? In other words, the work associated with force is always equal to the force times the distance, only in the special case that the force and the displacement are in the same direction. If I take a car and I push the car, the work done by that pushing force is equal to that magnitude of that force times the distance I'm pushing forward, because both the force and the thing, and again, that comes from the fact that the angle between the two forces is 0, the cosine of 0 is 1, so you're all set. On the other hand, if the force is anti-aligned, which is to say anti-parallel, then the work done is the same thing, but now instead of cosine of 0, it's cosine of 180 degrees, which is -1. The work done is negative F times delta x. So in other words, if I'm pushing the car and the car is going forward, I do the work of push on the car. The work on the car due to that force is positive. But if the car is pushing me, then the work that I'm doing on the car, I'm pushing the car, but the car is coming towards me. If the car is pushing, is as a result of that that shoving, is that the car is winning and I'm backing up, then the work done on the car is negative. I always ask the question, the direction of the force on the body that you're interested in, that work done by that force on that car for negative displacement, right? And finally, if sort of run out of room here, so let me tuck it into this corner. If the force is perpendicular to the displacement, delta x, in other words, the body is moving, but I'm pushing on it sideways, then the cosine of 90 degrees is 0. So the work done is equal to 0. So no matter what, if the force is perpendicular to the displacement, and it turns out this is true whether the path is straight or not, because it's true at any infinitesimal point. If the force is perpendicular to displacement, then the work done by that force is 0. I'll say that again. If the force is perpendicular to the path, then the work is done is 0. That turns out to have many applications. Often the path could be complicated, or there could be all kinds of crazy things going on with the force. As long as the force is perpendicular to the path, the work done will be 0. And that's always good. All right, so that's all we have about work.